Okay, so in reviewing your lab, you were asked to graph two things, current, or voltage versus current, with current being the independent variable, which, as a reminder, means that current goes where?
On the x-axis.
On the x-axis. The current down here, and we measured it yesterday in amps, and voltage in volts on the y. And what I saw from most of you, this is almost a foolproof. Shoot. No, come on. Almost a foolproof lab. Most of you, maybe all of you, got a line that looked something like that. So in the conclusions and the analysis part, I asked you to find the slope of this and then use that to write the formula. So let's say you had a slope of some value here. I don't really care what. It is meaningful, but each of you could be different. When we have a line, what's the general formula for a line? Y equals mx plus b. That's swell in math, but it's not physically meaningful to us. So instead, in science, when we've taken the time to draw a graph like this, instead of x and y, we actually put in what symbols for those values. So our y is over here. That's voltage. What's the symbol for voltage? V, thank you. Okay, the m, that's going to be some number. I'm just going to leave it as a little m. That's our slope. X is down here. It's current. What's the symbol for current? That's the abbreviation for the units. The symbol is I. Okay, and then we have this B. What does this B mean in math? The Y what? Intercept. It's where this line crosses the Y. Now we might be able to do that through inspection, but we can just reason it out physically too. When you have zero voltage, so zero batteries, how much current would you have? Zero. So you'd have, for this part, 0 is equal to some number times 0 plus B. So what must the value of B be? We solve this red equation for B. What does B equal? 0. It has to be. So there is no y-intercept. We don't have to put anything. This would be our formula for our slope with whatever value you found for the slope as an actual number. So that's actually significant. That's part one of the conclusions. Part two asks, let's see. Part two asks you to replace that. Oh, that's easy. Okay. The relationship here is Ohm's law. So all I want to do now is, instead of just using two symbols, I want to see if I can use all symbols rather than just a number there. Replace x and y variables for the best fit line with letters representing voltage, current, and resistance. Well, we found where voltage and current went. We haven't found anything for resistance though, right? What did you find? What do you think? Where does it go? And does that make sense? So Emily, what did you calculate for your slope? 23.3. That's really close to another significant number in your experiment, I'd be willing to bet. If you flip back to your data table, do you see a number that's actually pretty darn close to that? What value is pretty darn close to that? Yeah, 25 ohms, that resistance. Caleb and Jeremy, I saw your numbers. Yours were just slightly different. Somebody had 11 or so, and somebody had 12 point something, I think, right? What was the value of your resistor? 12 ohms. That slope of this graph is our resistance. I can actually, slope is actually the resistance. So Ohm's law is this, but instead of M as just a numerical slope, we actually know that it is R, the resistance. This is something called Ohm's law. And that's, we're going to talk briefly about that, and then you're going to have work time. Let's see if I can scroll down. You're not cooperating very well with me. So, in your notes, put a small section for Ohm's law. Ohm's law is that relationship. It is the most important electrical rule there is, and it works in almost every single electrical case, possibly every single one. We usually rearrange it just slightly and flip those last two to be V equals I times R. But if you put R times I, that's fine. You'll sometimes see it I equals V over R. It means the exact same thing all the time. V, just like up above, is our voltage in volts, which is a capital V. What does voltage mean in a circuit?
Potential energy that pushes electrons from one place to another.
So this is the energy pushing the electrons. I, as we said above, is current in amps or amperes, abbreviated with a capital A. What does current represent in the circuit?
How fast is flowing?
How fast it's flowing. So essentially how many electrons are going through. And then R, our last term here, is the resistance, and that will be in units of ohms, which is abbreviated with the Greek letter omega. What does resistance, or what does the number in ohms represent? What does resistance mean? Yeah.
Measure of the opposition to electron flow.
It's the opposition, right? It's how hard is it to get through. So what this rule is saying is that depending on how hard you push, you get a certain number of electrons based on how hard it is to push. So the harder it is to push, the fewer electrons you'll get. The easier it is to push, the more electrons you get. And these are always going to be related in this way. So this is a very, very important one right here, which will be the main formula for our whole chapter. And we're just going to be, the rest of this is just now figuring out different ways that this applies, or different ways to apply it to a little bit more complicated things. Your homework is just going to be, it's only 8 questions because there's only so much I can ask you about. It's just going to be interpreting some different circuits or some descriptions of circuits to find one of those 3. So we've done that sort of math practice lots before. I'm not going to hold you up anymore. If you remember all of this, you should be good to go. Homework 5.1 is 8 questions. It's due tomorrow when you come into class so that you're ready for the lab.